All right, we are going to talk about investigating and analyzing functions. So there are 6 of them here in your notebook. We are going to go through 4, 5, and 6, and then hopefully you'll be able to go back and do 1, 2, and 3 once you've seen how to do these. So first thing you want to do is take a look at the function, the equation that's given to you, and analyze it for, what type of function is it? So when we look at this one, we see absolute value bars around the x, and so we recognize this as being an absolute value function. And so under name, that's what we'll put. Mathematicians aren't super creative, so they just name them after the prominent operation going on. Locator point. So if you remember A, H, and K from your Honors Algebra 2 classes, remember, A is always out front being multiplied by the function, H is always being subtracted from the x inside of your prominent operation in that function, and then K is always outside being added or subtracted. And H, K are the coordinates of your locator point. So in this case, H is positive 5, K is positive 1, so your locator point is 5, 1. That is the vertex of this absolute value function. And so we'll go ahead and plot that right there at 5, 1. Remember that an absolute value, when graphed, always creates a perfect V shape. And we can think of the A value as being like a slope for it. So here A equals -1, meaning this is concave down or face down, and we'll go down 1 over 1 in each direction in order to create this graph. And so it would continue like this forever. So there's our perfect V shape. For x-intercepts, we're seeing it touch the x-axis in 2 spots, right here and right here. So this is 4, 0, and 6, 0. Y-intercepts, so where it touches the y-axis, we see that right here, and that's 1, 2, 3, 4 down, so 0, -4. Domain, so domain describes a graph from left to right. What we see is this graph is continuous from left to right. It's going to continue forever this way and forever that way. So the domain is everything. There aren't any x values that cannot be used in that equation. There's no blank spots in our graph. Remember that range describes a graph from bottom to top. So these arrows mean it's headed all the way down to -infinity. So we have to describe it from smallest to largest. So -infinity all the way up to, this is the highest it ever goes at 1. So we will say -infinity up to 1 with a square edge bracket around 1 since we actually have a point there. This graph is continuous from left to right. So it's continuous over the entire course of the graph. For increasing and decreasing, put your finger on the left side of the graph and just follow the graph and describe where you're headed. So I'm headed up, but then suddenly I'm headed down. So this portion is increasing, this one is decreasing. So it's increasing, and remember we're describing this with domain intervals from left to right. So it's increasing until right here at 5, and then after that it is decreasing. And we're always using parentheses here because at 5 it's not increasing or decreasing. It's our point of, it's a maximum, which we can actually go ahead and write down. It's the absolute maximum for this function is the vertex since it's concave down. And so it's changing direction there. There's no place on this graph that it's constant. It's not flat anywhere. So NA, it's bounded above by y equals 1 because I could draw this horizontal line and it would never go above it or cross it. Remember, that's what bounded above or below means. Can we draw a horizontal line?
The following CLC, please make your way to the auditorium. Crump, Daniels, Dar. Again, Crump, Daniels, and Dar. Thank you.
So bounded means can we draw a horizontal line below the function or above the function that it would never cross. So we can above this function. We can't below because these downward arrows means it's continued downward forever. So it's only bounded above. It does not have a minimum since it continues on forever down to negative infinity. It does not have any asymptotes. It's continuous from left to right. No, doesn't level out to anything. Symmetry, it is symmetrical. If we would draw its axis of symmetry, it's right here. So x equals 5 is our axis of symmetry. And then for end behavior, so remember, you write LIM for limit. Under LIM, you describe the x. So the first one is x goes to negative infinity of the function, and it has to be written exactly like that. These all stacked on top of one another, then f of x, and then equals. So if I look at the left side of this graph, it is headed down to negative infinity. And then I also need my other end behavior statement. So that describes the left side of the graph, and that the left side is headed downward. Now I've got to describe the right side. So again, limit as x goes to infinity of the function. And again, if I read this graph, the right side here is headed down to negative infinity as well. So both the left and the right side of this graph head down. So that is a function investigation. We identify the name, we create a graph, we identify locator point. So for absolute value quadratic functions, they both have a vertex. It's either the highest point if it's concave down like this, or it's the lowest point if it's concave up. We identify intercepts, so x-intercepts, also known as the zeros. The y-intercept, where it touches the y-axis. Domain, so describing the graph from left to right. Range, describing it from bottom to top. Talking about continuity, so can I draw it without picking up my pencil? If not, where do I have to pick up my pencil and why? Where is it increasing? Where is it decreasing? Does it stay constant anywhere? Boundedness, so can I trap it under a horizontal line or above a horizontal line? Does it have a maximum or a minimum? Asymptotes, so are there any vertical asymptotes or horizontal asymptotes that we level out to? Symmetry, so could we cut it in half anywhere? And then end behavior, where does the left end and the right end head? All right, let's check out the next one. So number 5 here, right away looking at it, I identify this is a cubic function. It's being raised to the 3rd power. Locator point, again, is hk. So h here is negative 3. K is negative 4. So we plot that point, negative 3, negative 4. And then with cubic functions, the graph looks like this, kind of like a stretched out S. And you always have 3 points on the diagonal here, and then it stretches up and stretches down. So the 3 points on the diagonal, as long as A is 1, which it is in this case, we'll just go up 1 over 1 and down 1 over 1. But remember, you can always create a table of values. We know that our locator point is at negative 3. Negative 4. So if you just try a couple of values before it, I'm going to plug in negative 1. If you plug negative 1 into the equation, negative 1 plus 3 gives us 2. If you cube 2, you get 8 minus 4 is 4. So we can plot negative 1, 4. If we plug in negative 2 plus 3 is the negative 1. Cubed is negative 1. Take away 1 more is negative 5. Sorry, that would have been positive 1. That's negative 2 plus 3 would give us 1. 1 cubed is 1. Take away 4 is negative 3. Sorry. Did that backward, and so that's why we're seeing it right there at negative 2, negative 3. Again, negative 3 plus 3 would be 0. 0 cubed is 0 minus 4. It gives us that negative 4. If we would plug in negative 4, negative 4 plus 3 would be the negative 1. Negative 1 cubed is negative 1. Take away 4 more is negative 5. So that's why we see this point right here. And then if you plug in negative 5, negative 5 plus 3 would be negative 2. Negative 2 cubed is negative 8. Take away 4 more would be negative 12. So it'd be about 2 blocks off the grid down here. And so we can sketch in our cubic function. All right, so x-intercepts. We can see that it's touching here. We need to know what that value is. Remember, we reviewed how to find x-intercepts. You replace the y or the f of x with 0, and then we just have to use our algebra skills to solve. So I could add the 4 over, but then I've got to undo the cube, so I've got to take the cube root. And then we could subtract the 3. So we'd have -3 plus the cube root of 4. And you could type that into a calculator if you wanted to estimate it with a decimal, but this is also acceptable. That's your exact answer. Y-intercept, we don't even see it on the graph, so plug in 0 anytime you want a y-intercept. Whichever intercept you're trying to find, you make the other letter 0. So because I now want a y-intercept, I replace x with 0. So we'll end up with 3 cubed. So we'll get 27 minus the 4 gives us 23. So we've got a y-intercept at 0, 23. All right, domain from left to right. This is continuous. Oops, sorry. It's going up. Stretches out forever left, forever right, and bottom to top. So domain and range are everything. Every odd polynomial, the domain and range are -infinity to infinity. This is continuous everywhere, so over the entire course of the graph. It is increasing the entire length of the graph. If I read that with my finger from left to right, I'm headed up the entire time. So nowhere on this graph are we decreasing or remaining constant. It is not bounded because it's headed down to -infinity and up to +infinity, which also means it does not have a maximum or minimum value. It does not have any asymptotes. There's no vertical breaks. It doesn't level out to any horizontal value. It's not symmetrical. We could find a point of symmetry. So it doesn't have a line of symmetry. We could say that it has a point of symmetry at that locator point that we could flip over. If we describe end behavior, so remember the limit as x goes to -infinity of our function. Well, the left side of this graph, I'm headed down. So the limit would be -infinity, whereas the limit as x goes to infinity of our function on the right side is +infinity, because on the right side we're headed up to +infinity. All right, so there's our second function investigation. We'll run through one more, and then hopefully you'll understand what you need to go back and do those first 3. So number 6, if I take a look at this equation, I see the square root. So this is a square root function. Again, locator point, hk, so h is -4, k is +3. So we plot that. That is our locator point, starting point for our graph. A here is -2, so it's going to be headed downward and stretched. We want to be strategic about what x values we choose, because we have to take the square root. So like 0 was fine because 0 got us 4 underneath. The square root of that was 2 times -2 is -4 plus 3 would give us -1. So we know 0, -1 is going to be on the graph. But we wouldn't want to plug in like -1, because if we plug in -1, I'll get 3. I don't know what the square root of 3 is. It's not a whole value. Same thing, -2 will get us 2. Again, square root of 2, not a whole value. If we do -3, that one will work out okay. Because -3 plus 4 gives us 1. Square root of 1 is 1. Times -2 gives us -2. Plus 3 gives us 1. So we can plot -3, 1. And then, we knew the locator point. -4 gives us 3 because -4 plus 4 is 0. Square root of 0 is 0. Times -2, 0. Plus 3, 3. So that was that point. We wouldn't be able to go any further than that, because if I tried -5 for x, -5 plus 4 would give me the square root of -1, which is I. It's imaginary. It would not exist on a traditional graph and grid. So there is nothing over here. It only continues in this direction. The next value that, in the positive direction that I could do would be like 5. If I plug in 5, 5 plus 4 is 9, square root of 9 is 3, times -2 would be -6, plus 3 would give me -3. Yeah, I wouldn't want to choose any in between there. I'm trying to get perfect squares underneath. So 0 got me 4 underneath, 5 gets me 9, next one I'd be going for would be 16, and so on, so that I'd have perfect squares under there that we could square root to get nice whole values. That was a little rough. I'll try one more time here. Alright, so there's your negatively oriented, stretched downward square root graph. X-intercept, again, we can see it crossing the x-axis, but it doesn't appear to be a whole value, so we need to solve for it. So to find an x-intercept, we're always replacing the f of x or the y with 0, and then using our algebra skills to solve for x. So I subtract the 3 over, divide by the -2, and then we'll square both sides to cancel out the square root. So we'll have 9/4 equals x plus 4. Well, we'd need a common denominator, so 4 is really 16 over 4.
The next set of CLCs to the auditorium, please. DeMarzo, Mrs. Detweiler, Mr. Detweiler, Donner, Eisenbiel. Again, DeMarzo, Mrs. Detweiler, Mr. Detweiler, Donner, Eisenbiel. Thank you.
So if we get a common denominator, so 4 is really 16 over 4, so that we can subtract 9/4 minus 16/4 gives us 7/4. And so that's our x-intercept. Remember, for the y-intercept, we are taking our function and replacing the x with 0. So we get -2 times 2 plus 3. So -4 plus 3 gives us -1 for that y-intercept. Domain, well, it doesn't exist over here. So it has a definitive start point here at the -4, and then it continues forever to the right. So -4 gets a bracket. Since we actually have a point there, we can use that. We can equal -4 in the equation. Range, it's headed down to -infinity, and we always got to describe it from bottom up to top. So we'll say starts at -infinity, comes up to this high point at 3. So -infinity up to 3. This is continuous, but only from -4 to infinity, where it exists. This graph does not increase anywhere. If I read this from left to right, it's going down the entire time. It's not constant anywhere. I can't bound it below because this arrow, it's going to keep going down. So I can't bound it from the bottom, but I can bound it. I could draw this horizontal line here and it would never go above it. So it's bounded above by y equals 3. The maximum is that starting point at -4, 3. That's the highest it ever goes. It does not have a minimum because it continues forever downward. It does not have any asymptotes. There's no vertical breaks, no horizontal line that's leveling out to symmetry, no. For our end behavior statements, so again, LIM for limit. Underneath LIM, you have to describe the x. So x goes to -infinity of the function. So the left side of this graph, the limit does not exist because it doesn't continue over here to -infinity. So that's what we say. If the left-hand side does not continue, we have to say the limit there does not exist. On the right side, the graph continues forever, so we can talk about the limit as x goes to positive infinity. This one's headed down to negative infinity. So as x goes towards positive infinity, the function itself is headed down towards negative infinity. So the y value is headed down to negative infinity as we move to the right. As we move to the left, we get stuck. We can't move to the left. We can't go over to negative infinity. So dne does not exist. And we abbreviate does not exist with dne. All right, hopefully you're feeling pretty good about function investigations. Go back and try problems 1, 2, and 3.